Sorry, I didn't get you. Are you speaking? Welcome, Juliana. Welcome, John. Then welcome, Sally. Starting shortly. All right, it's 5 p.m. already. I believe we can, at least we have a number of persons on call already. So I believe we can start now. Okay, it's 5 p.m. in Nigeria and it's 7 p.m. right now in Uganda. Yes. So, Andrew, I think we can start now. You can go on sharing your screen and taking us through the session. Welcome once again, everyone. I trust we're going to have a lovely session. Thank you.
Hey, thank you, Paul. Hello, everyone. Thank you all for joining in, wherever you're joining in from. and you are most welcome to this very technical lecture of ours. And our topic today, we shall be looking at leveraging geothermal energy for sustainable low carbon economy. Our technical lecture is brought to you by SPE Wari section in collaboration with SPE Uganda section. My name is Andrew Kirunda. I'm a drilling engineer working with CNOOC International and the YP section chair for SPE Uganda section, and I'll be your moderator for this lecture today. Hey. Today's lecture will last for about 1 hour and some few minutes. So we encourage all of you to ask questions, to go into the chat and type any comments such that we can actually pass them on to the facilitator to take us through them during the program. And allow me to briefly walk you through our agenda today. We shall have a safety brief, opening remarks, an introduction of the guest speaker, the professional lecture itself. Then we shall go into the questions and answers. Thereafter, we shall have a photography session and then presentation certificate together with the SPE awareness and upcoming events. And then we shall close the program. So before we proceed any further, let's have a quick safety brief from Sydney Nasanga, who is our YP member from SPE Uganda section. So Sydney, I can see already in the call. Please give us the safety brief and we proceed. Thank you.
Okay, thank you. Good evening, all protocol observed, and thank you to all those who have been able to join us today. My name is Nasanga Sydney Angela, a member of the SPE Uganda section, and I'm going to take us through the SPE safety moment with the mantra, think safety first. Okay. So during this meeting, please mute your microphone unless you're given permission to speak by raising up your hand to ensure orderliness during the course of the webinar. Also, please ensure that your volume is set at a reasonable level so as to ensure that you can hear the fire alarm in the event of an emergency. Also, please utilize the chat button at the bottom of your screen where you can submit any comments or questions that you may have during the course of this webinar. And during the course of this webinar, please maintain a good posture and always remain alert and aware of your surroundings. And with that, I thank you once again and leave you with a reminder to always stay safe. Thank you.
Thank you very much, Sydney, for that very timely safety brief virtual program we are having today. Next on the agenda, we shall have the opening remarks from Engineer Gideon Chibirige, who is the section chair for SPE Uganda section. Engineer Gideon, I can see you already on the call. Please, over to you.
Yes. Thank you very much, Andrew. And thank you very much, Sydney, for that very good safety brief. So please just confirm if you can hear me. Andrew?
Yes, we can hear you loud and clear.
Okay, perfect. Good evening, distinguished members of Society of Petroleum Engineers, Uganda section, and our esteemed collaborators from SPE Wari section 104, young professionals, industry partners, and all participants joining us virtually, all protocol observed. My name is Gideon Chibirige, and I serve as the servant-in-chief of SP Uganda section, and it is my great pleasure to officially open this collaborative technical lecture. And I want to just give a warm welcome to our speaker, Israel Momo, who serves as the treasurer of SPE OSU, that is Oklahoma State University chapter, and also to give a special thanks to our moderator, Andrew, my very own vice chairperson, YP chairperson of SPE Uganda section, and also a special appreciation to our collaborators, Dr. Adetona Oluwaseun, who is the section chair of SPE Wari, and Lucky Emimi, I don't know if I've said that correctly, YP Chair of SPE Wari, for making this cross-sectional knowledge exchange possible. So tonight's topic, leveraging geothermal energy for a sustainable low-carbon economy, comes at a very critical juncture for us over here in Uganda, in East Africa. As Africa advances its energy agenda, geothermal energy presents reliable, clean, but also indigenous pathway to reduce carbon intensity, and while at the same time supporting economic growth. So we believe that this session will explore practical insights, innovative applications, and collaborative opportunities across our region. So we look forward to learning a lot from Mr. Momo. And I believe that by the end of this session, we shall have learned a lot and we shall be looking to apply some of what we have learned. So let us begin with anticipation and a shared commitment to sustainable energy solutions. And ladies and gentlemen, I now declare this technical lecture open. Thank you very much, and over to you, Andrew.
Thank you very, very much, Engineer Gideon, for those warm and welcoming remarks. So we shall move on to the next item on our agenda, and that will be introduction of our very own guest speaker. And I was asked to allow Paul to do the introduction. So Paul, I'm going to hand over to you to introduce this esteemed guest of ours.
All right, thank you so much, Andrew. Please confirm you can hear me.
Yes, loud and clear, we can hear you.
All right, thank you very much for giving me the opportunity to introduce our esteemed guest speaker. Yeah, and this session is actually power packed. By the time I'm done with the introduction, I believe you will understand where I'm coming from. So let's get to know our speaker. So Israel Momo hails from the southern Nigeria and is currently a graduate student in the Department of Petroleum Engineering at OSU, that's the Oklahoma State University. Israel completed his bachelor's degree in petroleum engineering from the Federal University of Petroleum Resources, Nigeria, where he served as the vice president of the Society of Petroleum Engineers, SP student chapter. Then he joined OSU, that's Oklahoma State University, in 2022 and has continued research in developing a proof of concept for the flow of ionic liquid in enhanced geothermal systems. His interests include the experimental, analytical, and numerical analysis of coupled fluid and particle flow through various types of rock fractures, employing computational fluid dynamics and discrete element methods, tools for analysis. Since joining the program, he has participated in the SP Geothermal Datathon in 2023 as part of the ThermoSeekers team and engaged on campus with other societies, including the American Association of Petroleum Geologists, AAPG, and the American Association of Drilling Engineers, AADE. Now, Israel currently serves as the treasurer of the Society of Petroleum Engineers of Oklahoma State University student chapter, and has served as the 2023-2024 president of the chapter, winning an award for retaining and engaging membership. His goal is to revive student participation within the chapter by developing engaging activities. He hopes to work in the industry as a specialist in coupled fluid and particle flow simulation for geothermal and conventional fractured system. So with a resounding ovation, with a virtual ovation, can we give it up for our speaker? But before we, while we are doing that, like I mentioned, this session is going to be packed because his advisor is currently on call also and is going to be joining in the presentation. So this is a one-of-a-kind presentation. And we're going to just do a brief introduction of his advisors also, so that when it comes up, it won't have to do that again. So permit me, I may not get the pronunciation well. So his advisor is Unjuki Lee, is an assistant professor in the petroleum engineering program in the School of Chemical Engineering at the same Oklahoma State University, like I mentioned, and the faculty advisor for the OSU SP student chapter. So he has a BS in civil engineering from Seoul National University, South Korea. He received his MSc and PhD in petroleum engineering and from the University of Texas at Austin. He worked as a postdoctoral fellow in the Center of Subsurface Energy and the Environment and Environment at the University of Texas at Austin before he joined OSU in 2021. Now his research focuses on reservoir geomechanics and hydraulic fracturing, including rock fracture mechanics, hydraulic natural fracture interaction, drilling-induced fractures, reservoir compaction and inflation, induced seismicity, and enhanced geothermal systems. So like I said before, with another ovation, virtual ovation, let's give it up for Sir Unju P. Lee. So while we're doing that, I think at this point, we'll just hand over to our guest speaker, Sir Israel Momo, to take over the presentation. Thank you so much, everyone.
Hello, thank you, Paul. Thank you, everyone. Thank you, Andrew and Gideon and everyone who has introduced us. I will just try to share my screen. Please confirm you can hear me clearly and okay.
Yes, louder, please.
Okay. Can you see my screen?
Yep.
Yes, we
we
can see
can.
you.
Okay. Thank you once again for the introduction. Today, I will be talking on leveraging geothermal energy for a sustainable low carbon economy. And I know I'm presenting to the Warri and Uganda section. As Paul has rightly introduced us, you can reach out to us via any of the contact listed. So the presentation is going to follow this outline. I'm going to introduce what geothermal energy is and what it means for the energy portfolio for any country or anybody who wants to apply it. And then we're going to look at the global energy mix and probably focus on some specific countries and on Africa. We're going to try to define what a low carbon economy is. And then we're going to see how geothermal energy is very visible in the Nigeria and Uganda geology. We're going to then discuss the forms or methods by which we can utilize or explore these resources. I will focus particularly on EGS. Don't worry about the acronyms you've seen. By the end of this talk, you would understand what they mean. I'm going to focus specifically on EGS because it's partly what I've been working on. And then we're going to see what sustainable energy future really means for both Nigeria and Uganda and for Africa as a whole. And then some conclusion and questions. I'm looking forward to an engaging discussion. So what is geothermal energy? Geothermal energy, the word geothermal is derived from two words, geo and thermal, which means earth and heat. So it's basically the large amount of heat energy that is buried within the Earth's surface. As you can see in this picture, we believe the Earth has a harder core. So from the core to the surface on which we are standing, there is temperature gradient, there is temperature increase as we go closer to the core, and we are trying to explore this concept. For example, in the United States, where they have a very developed temperature gradient map, you can see that there is temperature distribution. So this map is showing temperature at 10-kilometer depth at different locations around the US. And the black dot you see where they're actually exploring hydrothermal resources, which is a form of geothermal energy. The black dots you see are like wells where they grade or they're utilizing hydrothermal resources. So This map is developed for a 10-kilometer depth, like I said. So it depends on the depth and how far you go. You can get as high temperature as you want. So this is an example of the Earth. So beneath the Earth's surface, we have heat energy, and this heat energy can be converted to various forms of energy. It can be used to generate electricity. It can be used for space heating, industrial processes, and the advantage of this is that you have very low carbon footprint. The implication is that you have less, you kind of have more, or like a more diversified energy portfolio and more renewables in the amount of energy that you are using. So for developing countries, like most countries in Africa, we have two options, because this newer technology or newer renewables require newer technology. We can either advance our technology really quickly or adapt technology from this developed nation, or we can rapidly consume fossil fuel to meet our demand for energy. So whichever determines if we're in a low carbon economy or if we are in a high carbon, technically, where we just emit carbon irresponsibly, kind of. So but that's not the case. So we'll have two options. I'm just putting that on the table right now. um so industrialization and income growth correlates directly with energy consumption. What I mean is, if we look at what each country is producing currently, based on a global map, we're going to see that the most consumers of energy are actually more developed countries like USA, China, Russia. You see that the more you consume, the more you kind of, it's directly correlated to your industrialization and your income or wealth. So why are we focusing on geothermal? We're focusing on geothermal because we don't just want to consume irresponsibly. We want to consume with a sustainable energy in mind, with a sustainable environment in mind, with a better energy mix in mind, with a better economy in mind. So, what is the state of the consumption of energy globally? Is everybody moving away from fossil fuel and just focusing on renewables? Um, so if we look at the global energy mix, what the global energy mix mean, what percentage of energy consumption is coming from what source, we will see that they've been consumption from traditional biomass like wood and all, and coal, and then oil, natural gas, nuclear energy. You see that until the 1950s, we had pretty low consumption of fossil fuels like coal, oil, natural gas, and the rest. But currently, it we've added those newer fossil fuels since 1950, as you can see. And since then, we've kept adding newer sources like nuclear and hydropower, but we've not exactly stopped using what we've been using. In fact, coal is globally increasing, as you can see on the map, and oil and natural gas, they're all increasing as we are growing. This is not only about what you want to consume. Population is also a factor in it. If we look at what the population is as at the time oil was discovered, you see that the difference between 1870 and the 1950s, there is this exponential increase. And then by the factor that population increases, energy demand doubles. If you see here, by 2022, we had about 8 billion people. So that was the 3 times increase from what it was before. And then you have double that's 6 time increase for energy demand. So population growth also is a factor. So as the population grows, there is more demand for energy. So how do we want to meet this demand? How do we want to meet this demand? We determine if we're going towards a low carbon economy or a high carbon economy. So a low carbon economy, I would define, is an economy with the right mix of energy supply source, advanced tools enough to manage and contain emissions, and deliberate industrialization that ensures environmental sustainability at the minimum emission, at the most minimum emission. This would demand collaborations from government stakeholders and private entities to make the right policies, government and private institutions for capital investment, because there is going to be some kind of investment needed, research institutions to be at the forefront of the application to ensure that technologies that are being developed and researched are adopted in the field, into field cases, efficient land and mineral use, where you have really nice warm springs and surface occurrences of geothermal resources. How do you use these things? Who owns them? Is the government? How do you manage them? So these are all the things that come into play when you are talking about a low carbon economy. Now, if you look at the energy mix for like an advanced or a developed country like the United States, it has everything. It has a mix of everything. However, if you look at the tail end of the map on the top right for the United States, you see that the use of coal is gradually decreasing and the use of natural gas is gradually increasing. Natural gas is a much cleaner energy source than coal. So it's not exactly phasing out coal, but it's slowly replacing it with a better option. Now, if you look at that of Nigeria, you have just gas and hydropower as the major source of electricity generation. We could do better. If you look at South Africa, you have coal, you have a mix of nuclear, you have some wind, and you have some solar, which is a little bit more diversified. And the whole of Africa, I just showed Africa to show that, like Gideon mentioned, Africa is actually growing in terms of energy demand. So it's going to continue increasing. So whether it increases towards a low carbon economy as a continent is dependent on how diversified that portfolio is and how it can take out fossil slowly, replacing it with cleaner sources of energy. So according to the Nigeria Energy Transition Plan, by 2060, the country should reach net zero carbon emission. So is this feasible? And how is it going to be feasible? It's going to require a lot of contributions from the entities I just mentioned: government, private entities, research institutions, and even the people themselves. So we can see that this is important because the increase in energy portfolio and the increase in energy consumption by a nation is directly proportional to its wealth. If you look at this map here, I borrowed it from the slides from the immediate past president of the SPE. You see that the amount of energy the country consumes per population, this is a normalized map of GDP per capita and energy consumption per capita. So it's divided by population. So you see that the amount of energy or the wealth of the country is directly proportional to the amount of energy it uses. And there are no outliers. So for us to actually get going using much energy, we need to diversify and aggressively use that which we have. Countries like Iceland are basically using what they have, like geothermal energy, to do almost 90, 100% of their electricity. So you use what you have to reach that goal of increasing consumption and the wealth of the country. So aggressively diversifying our energy portfolio would gradually lead us to a low carbon economy. And remember, there should be a deliberate effort to contain emission and ensure that it doesn't become an irresponsible expansion or diversification, but a careful and deliberate effort to contain emissions. These are some of the surface occurrences or prominent geology sites in both Nigeria and Uganda where we have geothermal energy sources, which means it is possible to have geothermal energy in these places. It is possible. For Nigeria, I know of the Ikogosi warm spring in Ekiti, which is a very nice tourist site where people go and have fun and just relax. It's good, but we can do more. these are markers that are just, glaring at us and telling us that, hey, there is more, we can explore more and we can get more. These areas could be possible sites where we can explore geothermal energy. For Uganda, the government has a plan to a target for a 400 megawatt electricity generation, power generation by 2040 from geothermal energy. Uganda is seated close to the African Rift, the East African Rift, which is a very good site for volcanoes, and you have a very nice thermal gradient around that area. So you can actually explore geothermal energy in these areas. So both the Nigeria and Uganda economy stands a very good chance to diversify their energy portfolio. So I'm going to take us through the various forms by which geothermal energy can be harnessed and utilized for both power generation, space heating and cooling, and what have you. So first of all, I will take you through the ground source heat pump. There are two kinds of ground source heat pump. There's the air ground source heat pump and there's the water ground source heat pump. These are I'm going to take you by depth. So these resources are much shallower in depth. You can explore them at a shallower depth, and they're very unique because these pumps can help to take heat in and out of a building or take cold fluid in and out of a building. So let's say during winter, a building is cold. You want to transfer the cold air in the building out and then go to some warm spring and then exchange heat energy there, and the air coming back into the system or into the building is warmer. For water, you can use that water to indirectly heat the fluid you're using in the house for your kitchen sink, bathroom, bathtubs. These are ways we can use ground source heat pump. They don't require very large installation, and they can be scaled for one system, like a single building, and that makes it applicable to if the area has a very favorable geothermal gradient, then you can apply it in anywhere. You can apply it anywhere, basically. So that's the advantage. They are efficient. There's a long-term use of it, and it doesn't require so much maintenance. So you can actually use ground source heat pump where you have surface geothermal occurrences, like the pond you see in the image that I'm showing. So Ikogosi Warm Spring can be used for more while still serving as a tourist attraction center or what have you. The next form is the hydrothermal resources. Now, for this one, think about oil and gas reservoir, but it's filled completely with hot water. It's not as deep, but it's filled with hot water, and you can drill in. The reservoir pressure is just like favorable. You can produce that hot water to the surface, and then you can use it as power generation fluid in a turbine, and then you can recycle the cool water back into the reservoir. The reservoir permeability is high enough. Everything is just favorable. So you don't need to do anything. You just need to drill and produce. And this resource forms a very huge contribution in terms of geothermal energy in the United States. Like you saw the geothermal gradient map, you see those dots and everywhere. Those are hydrothermal resources. Now, this picture is arranged from left to right based on the initial temperature of the resources. Now, the initial temperature of the resource will determine what kind of plant you're going to install on the surface. So for a dry steam power plant, it has a much higher temperature and it's producing gas directly. You just run it through the turbine and then it cools down into a liquid and then you inject it back into the well. For a flash steam is a medium range temperature. There is a flash where you collect liquid and then it goes to the turbine. The gas goes to the turbine to drive the turbine, and then the liquid goes to the cooler and then back into the reservoir to get heated again. The turbine drives the generator for electricity generation. Then there's the binary cycle plant that requires two fluid. So it produces at a much lower temperature, and then the fluid is allowed to exchange temperature with something like a refrigerant. And then it produces a hot gas that turns the turbine, and then everything like that goes in a cycle. So the initial temperature of the reserve is also very important in the design of the power plants for the system. And now the final form of it is the advanced geothermal systems. There are two kinds of it. There is the closed loop system, which just requires, it doesn't need the fluid to touch to go into the formation. So you basically have a set of tubings that runs from the surface. It could go in a U loop, or it could just be like a Yeti cup, where the fluid goes through the annulus and then it gets heated up and then it goes up through the tubing to the surface and is produced as a hot fluid for heat exchange. These systems, advanced geothermal systems generally, makes it possible for geothermal engineering or geothermal energy utilization to be applied anywhere. Can you guys hear me? Hello?
Yes, we
Yes,
can hear you.
We can hear you.
Okay. Okay. So the AGS makes it possible for geothermal systems to be applied anywhere. It just depends on what thermal gradient of that place is and how deep can you go and how much technology you have to handle that temperature. How much can your tool handle? How much can your wall, can your pipes handle? So that's the unique system of the closed loop geothermal systems. Remember, the unique nature of this one is that the fluid doesn't get in contact with the reservoir. So it's just a closed loop system. You don't see the fluid in the system. The second type, and which is very promising, is the enhanced geothermal system. I'm going to say I'm a little biased to this one because I've been working on this a little more. So for short, it's called EGS. This one requires you to drill 2 wells. Just think of oil and gas wells. First of all, you drill 1 well into the reservoir. The reservoir is at a depth that the formation has low permeability and no fluid in it. So the difference between the EGS and the hydrothermal is that the EGS is much deeper and there is no fluid and no permeability in the rock. But the rock is at a very high temperature. So what engineers do is they fracture the rock and create fractures or pathways to flow fluid through the rock. Now, that's why it's called enhanced or engineered geothermal system. It means they've done something to the rock. And then you inject fluid through the injector, and then you drill a producer through the fracture system, and then you produce that fluid through the producer, and then you use it for power generation. This can be applied anywhere. So this is like a schematic of what it looks like. The fractures become like the main conduit for fluid flow between the wells. So the fluid goes in through the blue well and then goes up through the fracture, and then it's produced through the red well, which is the producer. We're going to just think of a single fracture case which can be solved easily. There are lots of publications on how to handle like fluid heat exchange between the fluid and the rock in a rock fracture, and how much heat can be produced in a span of 10 years from one fracture, and also how much power, which is power, how much power can be generated. I looked at the effect of flow rate, just telling you that there are some factors that controls the efficiency of these systems. They include the flow rate, the injection temperature, the fracture spacing, the spacing between the wells, the fracture aperture, and a lot of conditions like that needs to go into the design of the system. So we can see from the chart on the top right, it's a chart of outlet temperature versus time. The faster you flow, the less temperature you get at the outlet, because the fluid doesn't get enough time to get heated in the fracture. So there is an optimum design flow rate that you should be at, where you get enough temperature that you can use to generate power. And then on the lower right, you have the injection temperature parametric study on the outlet temperature. So the higher the temperature, the higher the outlet temperature you're going to get. This is because it's easier to heat a fluid that is already hot. So when the fluid is already at a higher temperature at the injection, then you're going to have a higher temperature on the outlet because it's easy to heat it. But what also controls what flow rate you use is the demand, what is being demanded at the surface or by the company who needs the heat, available surface equipment and related heating installation, nearness to the utilization processes. So for this system, it's always better to have your system, your utilization process closer to the system so you don't lose much energy in the transfer of the resource. The initial temperature of the reserve is also very, very important because it matters, because it can affect the performance of your downhole subsurface tools and tubings. The limitations of your surface equipment also is determined by the initial temperature of the reserve. And time is also important because things are changing. Temperature of the fluid is changing, temperature of the reservoir is changing, subsurface stresses are changing. So fracture dimension and everything is changing. So it's also important in your choice of parameters, flow rate, injection temperature, and all. So this is the interpretation in terms of electric power for a 10-year period. You can get up to 2.5 to about 0.5 gigawatt. And in 2021, Nigeria had about 11.7 gigawatt, which 74.74% was from fossil, which I assume is gas, and 26% from hydro. So we can add up to 2.5 gigawatt to 0.5 gigawatt of electricity to our 11.7 gigawatt of electricity if we are to explore geothermal for a single fracture at 20% efficiency. So what happens after 10 years? What happens to the fracture? Does it become uneconomical? And this is why it's called renewable, because the heat energy is always generated by radioactivity, and you can have energy, heat energy come back over time, right? You can always wait it out and it gets hot again and you keep producing. Um, so there are some challenges like early thermal breakdown, short circuits, where your injected fluid just rushes from the injector to the producer. It doesn't even get heated up because you have run through that part a long number of times, so many times it doesn't get heated up. The fluid just goes to the producer at the same temperature. That becomes a problem because you're not getting any heat from the reservoir. It's called a thermal drawdown, early thermal drawdown, or flow channeling. You also have concept of leak off, where the fluid just goes into the fracture and goes into natural fractures or fractures that are out of your domain or mapping that you didn't even know, and then you just lose those fluid and you don't get them back. There's problem with scaling. There's problem with proppant placement in the fracture, because as you move the proppant through the fracture. So I'm talking of proppant now for the first time, because when you fracture these reservoirs, you need to prop them. You need to put proppants in them to keep them open because they are under a lot of stress. And if you don't do that, they close down. So the fracture design is also important. You have to make sure that both wells are connected hydraulically, and that's where the fracture design comes in. The conductivity of the fracture is important. Time degradation, because the proppants are going to be crushed over time. What happens to the fracture conductivity? What happens to the volume of fluid you're producing because of that? So these are the challenges that are being currently faced in EGS, and I think my advisor is going to talk a little bit on them. Here are some of the solutions that we've proposed in the past and some other researchers have proposed. We have optimum facility design to strategically place the wells. You have thermally sensitive proppants to control flow channels. We mean proppants that can expand when the part is cold and then shrink when the part is hot to allow fluid to go, and then block a fracture when it's too cold. Thermally sensitive fluid that can thicken when the part is cold and be light or flowable, easily flow, less viscous when the part is hot. Then you have buoyancy driven fracture growth. And these are some of the solutions that have been proposed in the past to handle some of the challenges. And there is more to come as we keep advancing research. I'll let my advisor handle the rest of the talk.
Hello, thank you again for having us. Israel wanted me to continue or emphasize a little bit about our research effort in this area. and Israel has been heavily involved. Maybe that's why he's shy to talk about it himself. So he wanted me to chime in and introduce his work. So before I go to Israel's work, I'll talk about one project that we're working on to improve geothermal drilling, especially in drilling area. So as Israel said, um, the initial cost for EGS is a lot higher than unconventional or conventional wells because we're drilling through hot, hard rocks. And we typically want to aim for a bigger wellbore, which means we want to increase the contact area with the formation to recover more heat. So what we were thinking was can we utilize drill cuttings and analyze them to improve drilling? So this is one of the work my other PhD student is working on, is doing an image-driven drill cuttings analysis to improve drilling and also optimization for fracture locations. So that's what we're aiming for. This is in still a preliminary stage. We're working on it, and I'm just showing you some results that we have uh, that could show the potential of the work. So on the top, you're seeing the drill cuttings on the left, which we took picture with microscope. And then what we're trying to do is we're trying to develop a software using machine learning to detect the size of the drill cuttings, as well as can we get texture and shape and use them to predict what mineralogy is. So if you see on the right uh, bottom, I have two figures that is actually predicting the size distribution. So the top one is the size distribution with microns on the x-axis and the frequency on the y-axis. And also on the bottom, you're seeing the angularity from very angular, which means we kind of labeled them in a way to quantify. So star is the most angular shape that we can represent. So that will be close to 0, and circular will be 1. So we kind of looked at different type of shapes for each mineral and figured out can we categorize different type of minerals just by taking pictures of them rather than doing all the XRD and XRF. So our goal is to develop a machine learning framework that does all this, just taking pictures of drill cuttings, which later on we can implement a camera on the drilling rig. Just rather than doing mud logging, we can take pictures continuously to predict mineralogy all throughout the formation while drilling. So, and establish also static to dynamic correction. That means we're going to try to do a core analysis and compare it with the drilling prediction. And lastly, quantify formation mechanical properties and brittleness to help fracture design. So that's our first project working on geothermal, as well as we can apply this to unconventional as well. So that's where we're at right now for the first project. And the next one, can you go to the next slide, please, Israel?
Yeah.
So the next one is the work that Israel worked on during his master's for the past couple of years with me, which is developing alternative fluid or not ionic liquid to improve fluid hydraulics. Israel described really well what short circuiting is. So there are multiple fractures in the subsurface. As you circulate fluid, the formation will cool down. However, that kind of is not advantageous to us. It's even worse because as you circulate more, it cools down, then the fracture widens, so that the fluid that is cooled down, the fracture that is all cooled down will take all the fluid, which we don't want. So we were coming up with the idea, how can we detour all the fluids into hot fractures rather than the colder fracture? So we were trying to look at alternative fluids that will um, alter or dictate the fracture conductivity by changing the fluid properties based on the temperature. So this is the first set of work that DOE has sponsored. And what we're basically doing is we have a fractured core on the left bottom, as you see. We put that in a Hoax cell, and as you can see in the middle, which is the schematic diagram, and then we circulate fluid. So what we did is we circulated water first. So there are 4 charts on the right, which is different delta P's. So we have a different inlet and outlet pressure, but just focus on the bottom right, I guess the green one. So we circulate 10 minutes of water, which you see pretty consistent flow rate of 1.5 milliliters per minute. And then after 10 minutes, we inject the WBF, which is a water-based fluid, alternative fluid, to see how that can plug up the fracture. You see a flow rate drop because the fluid is a little bit thicker and it drops in flow rate because it's blocking the fracture, which we want to block the colder fracture, right? And then we re-injected water afterwards just to see how it recovers. So you see the flow rate is recovering back to its original state around 30 minutes. And we did that for 4 different pressures and also a lot of different fluids. I'm just showing you one, but that's basically we want to investigate the pressure drop from each type of fluid and see which one blocks the fracture better, but not also blocking, but also what fluid is recovering better to the initial stage. So that was Israel's work during his master's here. Now he kind of shifted. He graduated with this and then wanted to do PhD here. So and he said he doesn't want to be in the lab anymore, so he wanted to do more modeling. So we kind of moved. Well, I kind of put him in a modeling type of project, which is also funded by DOE. So this is basically developing proppants that survive under high temperature condition. So unconventional proppants, we just typically use sand, but unconventional temperature range is around 70 to 80 C, which sands are okay. It doesn't degrade too much, but in geothermal system, which is above 200 degrees C, you need a better proppants that survive under those conditions. Also for a longer time period, because we want to circulate the fluid for 30 years. So our task in this project is to understand how these developed new proppants could be transported well in the fracture. So our idea is to couple CFD, which is computational fluid dynamics, and DEM, discrete element method, to model proppant transport and fracture system. So CFD calculates fluid flow. I think Israel just turned on the video here. So if you look at the bottom right, you're actually seeing proppant being transported. So all the dots on the left are proppants injected at fracture. And you see I think this is a velocity profile, I think. But
Yes,
that's
sir.
what you're seeing the proppant settling to the bottom of the fracture. Now, what we're trying to assess is what should be the injection temperature and how does that impact the proppant transport? And also, if we were to change proppant shape or design, how would that improve proppant transport? So on the left, we're doing some preliminary study with single particle drop under different conditions. So the blue is a particle drop in room temperature, room pressure case. So you see a pretty stable linear line, which agrees with the Stokes equation analytical solution. Red is the same particle in the same fracture, but under high pressure and high temperature. Obviously, the high temperature causes fluid viscosity and density to drop, so you see the particle settling much faster. So we're doing a lot of analysis here. He has been working on it hard. So in the previous work, he published 2 conference papers. Now we're working on a journal paper. And this one as well, we're trying to submit a paper on single particle drop to ARMA next year, which is currently working on the abstract right now. I hope I explained everything. If I missed anything, Israel, you can chime in and explain about it. Thank you.
You didn't. Thank you, Doctor. So yeah, that's just the detail of how far we're coming with our own solution, and there is more. There is always room for more, and there's always room for better solutions. So a sustainable energy future for Nigeria and Uganda means a more diversified energy portfolio, government policies that favors the adoption of more types of energy and less use of fossil or more responsible use of fossil. And you can see on this map, you see where they have geothermal projects, EGS and AGS projects around the world. We need a dot somewhere in Uganda or somewhere in Nigeria. You can see Kenya is at the forefront of it in Africa. So we can do more, we can do better. It's just a question of how deep can we go and how far we're ready to invest our time, our energy, and our money to explore geothermal energy. Thank you very much. Thank you, Doctor. Thank you, everyone. We'll take question. One thing I didn't cover is the repurposing of oil and gas wells, which is also possible. Oil and gas wells with a little bit high temperature can be repurposed for geothermal energy. You can look into that. Thank you very much.
Thank you very, very much, Mr. Israel and Dr. Hunjo Lee for that very insightful lecture. Now is the time for us to jump into the questions. I'll begin by giving a chance to those who have joined, who have raised their hands. I can see we have Emmanuel Okupu. We shall begin with a question from Emmanuel. Emmanuel, please feel free to unmute. You ask your question. You look into the ones in the chat.
Oh yeah, thank you very much. Thank you very much, Mr. Israel and Dr. Lee. So very interesting presentation because it's an interest that an area that I'm also very much interested in, which is geothermal. So I just wanted to find out in terms of I know I don't know if I'm being heard. Please confirm that you can hear me.
Yes, we
Please.
can hear you loud and
Okay.
clear.
All right. Thank you. So we spoke more on the temperature stability of the propant, right? What research is being done on the wellbore integrity, looking at the fact that we are going to very deep wells with very high temperatures. So are there research interests? I know it might not be part of your research scope, but what can we do to ensure wellbore stability across those high temperature profiles? Secondly, also talking about the short circuiting when it comes to the fluid being flown from the injection fluid back to the producer wells. Is there like a huff and puff situation that can happen where we allow these fluids to soak phase, just like we do in cyclic steam, and kind of heat up for a longer period before producing the fluid?
Thank you, Emmanuel, for that question. I'll let my advisor go for the first one about wellbore integrity, and I'll try to answer the second one. Doctor?
Okay, so thank you for the question, Emmanuel. Wellbore integrity is a hot topic as well. Some conventional cements won't survive and lose integrity under high temperature. So there are people trying to include some nanomaterials or other type of material that will help survive hotter temperature. So there's obviously work going on in the wellbore integrity for sure. So that is ongoing and it is a hot topic. For the second one, we could do cyclic huff and puff and type stuff for sure. And I think Israel kind of talked about it where you can wait for a while and then wait till heat it up and then circulate to produce hot water. However, for EGS and for power generation, what we want is consistent production. So we can do that, but we prefer the heat being recovered not being continuous rather than cyclic. I can let Israel talk a little bit more about that.
Thank you, Doctor. That's what I wanted to say, because you have systems that are running continuously for heat. You may not want to do huff and puff in this case. You may want something continuous. Yeah. Thank you.
Okay, thank you for those responses. Our next question is going to be from Engineer Gideon. Yes, Engineer Gideon, please feel free to unmute and ask your question.
Thank you very much, Israel. Can you hear me?
Yes.
Yes, we can hear you.
Okay. Thank you very much, Israel, and as well to your supervisor, the doctor. And so there's something you mentioned, and you talk about OSU's DOE project that demonstrates the ionic liquids increasing viscosity at lower temperatures to block the fast flowing paths. And if I got this rightly, that would force fluids into hotter zones. Okay. And so my question is that for Uganda's rift system, Uganda has it is hot and dry rock, about 250 degrees Celsius, 3 to 4 kilometers. do these ionic leak formulations, okay, that you have mentioned, do they show optimal shear thinning at that temperature to enhance sweep efficiency without clogging the stimulated fractures? That's my first question, and I have a second one as well. But maybe you could first answer to that.
Yeah, thank you very much for that question. That's a really good question. So we've been doing a work on the rheology of the fluid, and your question is basically tied to the thermal stability of the fluid. And most of the fluid that we've tested are good enough to withstand those temperatures, still retain their flowability at those temperatures. And you're right, the blocking of the thicker fracture would actually force fluid to go through the hotter ones, thereby ensuring that energy production is continuous throughout the process. So yes, the fluid are stable, and that's the first criteria, or that should be one of the first criteria for the alternative fluid selection, to make sure that they are stable at the temperature of the resources.
Okay. That's very interesting. I don't know if you have actually, because this is quite new for me. I don't know if you've considered using these for other applications outside geothermal. I'm pretty sure there would be a hot cake, because normally what happens, for example, when you're trying to maybe induce some few fractures, I mean, we have formed some stimulated fractures, you want the fluid to move along the fractures and maybe block out the thief zones at the same time. So for me, this is very I found that to be very, very interesting, for
Yes.
sure.
Yeah.
Yes. Yes. Okay, so my next one would be about the AGS for sure, and mine, because we know that Kenya is among the biggest producers, our neighbors here. I think 85% of their power needs is coming from geothermal, and so they're doing a lot of, and we've been learning from our friends a lot about in advanced geothermal system, what you've called enhanced uh, EGS geothermal systems. So my question is that, of course, right now in Kenya, they're doing a lot of conventional hydrothermal. Basically, you have a hot, dry rock, and then you pump water, and then you try to produce that same hot water back, and then extract out the energy that you're extracting from there. So my question is about EGS, hydraulic stimulation, and is that something you think, based on the reservoirs uh, in Uganda as well, or even in Kenya, how can you have EGS in areas that have kind of a high risk of induced seismicity? For example, let's say you're trying to do EGS and then inadvertently, maybe you create bigger problems. Maybe you have subsidence, so you create more rifts. So how do you do that in a place that is quite more prone to seismicity?
Well, you raise a very good concern, and it's a good question. I will just answer briefly, but I'll let my advisor do more, because it's his main area. It's part of his area of research. So in EGS, one property of the reservoir rock is that it doesn't have a high enough permeability and porosity for fluid flow. So that's the difference between EGS and the conventional hydrothermal, where the reservoir has good permeability and pressure to allow fluid flow. So we need to create those fractures. And for this project we're working on currently, they have done a really good job studying and collecting sensors, like moments from the fracture program, where they can see how much disturbance is created from each fracture generation or each fracture plane. So these have been quantified and have been said that it's not that bad. It's not bad. It's not high enough to cause an earthquake or anything. So, we can measure those things on a richer scale, like how bad the magnitude of the quake is. So for hydraulic fracturing, they don't create that much magnitude to cause a large scale this thing. But it depends also on the geology of the area, right? So before you even want to create a fracture, you must understand everywhere around it to make sure that you're not interfering with maybe an active fault or something. But based on research and findings so far in EGS, they don't create that much magnitude that could cause an earthquake. I'll let my advisor add to that. Hello, doctor.
Yeah, that's a very good question. I'm glad you asked. That is a concern whenever you try to inject something in the subsurface, not just geothermal, but also wastewater disposal or perhaps CO2 storage. So whenever you increase pressure and disturb stress field or change temperature, that would cause stress reorientation and then possibly lead to fault instability and slip. So the first thing that you want to do is you want to characterize your geology really well in the region. Are there any faults that are critically stressed that might be potential slippage and then cause earthquakes? So that's the first thing you want to do. And also, you want to assess stress field as well. So you need to understand full stress field to actually categorize the faults if there are in risk or not. So there are a lot of analysis I can do to characterize faults that are critically stressed or not. That is a potential. I think they also call it fault slip potential. But yeah, those are things that you can do. And if you did all that and you still have concerns over earthquakes or other damages, I think that's why they're trying to develop a closed loop system where it's the advanced geothermal system where the fluid doesn't interact with the formation, then you just recover heat through the wellbore. Now, does that have no issues? Probably not, because it's still collecting heat from the formation, which leads to formation temperature to drop. And as you all know, if the formation temperature drops, all the rocks contracts and it also changes stress field. So not everything is safe, like as you do in oil production as well, because you're changing all the pressures and stuff. But there are a lot of efforts going on to understand, and you obviously need to understand the reservoir really well, characterize it really well, and understand the integrity of the wellbore as well as the reservoir to assess all these to operate geothermal system.
Okay. Yeah, thank you very much. Maybe my final one on that point, I mean, we've talked a bit about the risk. Some years back, I interfaced with a lady from, there's this company called Sage Geosystems, I think, Sage Geosystems, and they were doing, I think that's the first time I heard about EGS. But maybe I want you to just speak a bit to the economics of this kind of technology, especially in the US. I mean, we have seen it working in Kenya. I have not heard a lot of it happening in the US. How is the field looking like? What's the cost, for example, of energy when you use, or what's the, like, how we have incremental oil? Let's say you switch from conventional geothermal to EGS. What's the cost benefit of this? Because for me, it feels like, I don't know. Maybe is it still a research thing? Is it still in prototyping mode, or are there examples where this has been done and it is actually working? Say maybe they have drilled some kind of well. I think you called them these ground source heat pump or some kind of well. And then maybe at some point they started to add in these ionic liquids or something like that. So you're shifting to EGS, but what does the economics look like in such a scenario? What's the benefit of that? Thank you.
Yeah, I'll just talk briefly. I don't know if my advisor have points, but I'll also give him some time as well. So you're right, very correct. That's a good question. In terms of capital investment, it's huge because of the tool required in terms of temperature, because you want to be able to use tools that can withstand the temperature of your reserve. So the initial capital for this system is actually determined by the temperature of your initial temperature of your reserve, and as well as the type of surface facilities you're going to install. So there is always a turnaround time, a turnover time where you're going to start getting something from the resource. And yes, it has been applied to places, like I mentioned, places like geothermal, places like Iceland, Indonesia, Malaysia, and even the United States. They have mainly hydrothermal systems, though, that have worked. And places like France, Japan have some EGS project that have worked. And they face this problem as well, flow channeling. And that's why in the US, we have a very good research facility that has been installed and has worked. They have done flow for like 2 months, and it really gave them good results. It's called Utah Forge Project. You can look that up. The data is open source. You can see what they've done. But the turnaround time is not always going to be like 1 year or 2 year. Of course, that will be determined by how much capital you have put into it, right? And how and but the thing is, it has low carbon footprint, and the electricity generated from it is cheap. It's cheap, and the goal is to replace the base load electricity generated in the US with geothermal generation source. So yes, it has been applied and it works, but these challenges that we are seeking to answer every day through research is what will make it even cheaper and viable and applicable to every scenarios and everywhere, and make it even like comparable to how cheap natural gas and oil is. Doctor?
Well, I think Israel, you answered it really well, so I don't think I
Okay.
have anything to add.
Okay. Thank you.
Okay, thank you. Thank you very much for those wonderful responses. And thank you so much for the good questions, Engineer Gideon. Well, you mentioned something about costs, and I've been trying to appreciate the geothermal energy technologies. I'm just trying to come from the drilling standpoint. How do the geothermal wells exactly compare with the conventional oil and gas wells in terms of the design, the depth, and then also the costs? Looking at the fact that geothermal environments often may involve high temperatures and very corrosive fluids. So what technologies and materials are currently being used to ensure the well integrity and the equipment reliability during the operations and during the production of that hot water? Maybe if you could hint a little bit on that as well.
Yeah, thank you, Andrew. That's a good question as well. Yeah, in terms of cost, comparatively, I mean, that's controlled mainly by depth and temperature, right? Because the oil and gas wells are not having to deal with that much temperature compared to EGS wells or AGS wells. So the temperature is what actually contributes mainly to the difference, because the sorry excuse me, because your tools, your drilling bits, they have to be able to withstand that temperature for long. And mostly, I've seen mostly PDC designs for EGS wells, because it's mainly um, um, grinding, I think. So the tools have to withstand the temperature, and that's what makes it more expensive to drill. But of course, there are research going on to get better tools that can withstand this temperature and bring down the cost of drilling an EGS wells. And that's where research comes in terms of drilling. Doctor, you know.
Yeah, I agree. The only thing that I want to point out is that I think they're using more PDC bit than the roller cone because it's working much better. You drill much faster. Obviously, with the drilling cost, everything is about time. I know Fervo kind of reduced the drilling time by 1/3 in the recent past, I think 2-3 years to make geothermal feasible. So there's a lot of improvement going on. And also there are things that people are learning from geothermal they can apply to unconventional as well. So there's a lot of effort going on that helps both ways.
Thank you.
Okay. Thank you very much for that response. Just to follow up on that similarly, I'm just trying to see a lot of similarities actually with our conventional well designs together with the geothermal ones. If it comes to the casing design, do we still use the same conventional standard softwares like maybe a stress check, casing set, especially the stress check? Looking at the fact that the temperatures and also maybe the pressures that are going to be encountered as we are sealing our annuluses, our annuli. Do we still use the same standard softwares like stress check, or there are some a little bit of new considerations that you put into the design?
Thank you, Andrew, for that question. I've not looked into like the details of drilling software used for casing EGS wells, but what I'll say is there's always a requirement that whatever material should go in there for stability and integrity, those materials should be able to withstand the temperature of the formation for a long time without breaking down. But I don't know about like softwares that are needed to install the casing in place or make it like I don't know. But I think there's a lot of knowledge transfer from the oil and gas drilling to the geothermal systems. And like Doctor mentioned, there's also a lot of knowledge transfer that we're learning from EGS that are transferred into the geothermal, into the conventional system. But it all boils down to the temperature and how much your tools can withstand.
Okay, very, very interesting. Thank you for that response. Maybe I'll just have one last one from my end, then we can look at this in the chat. I think geothermal energy has actually been existing for decades now, but it still remains a little bit underdeveloped if we may compare it with other renewables. So from your perspective, what do you think could be holding back the large-scale geothermal adoption globally? And maybe in particularly here in Africa, looking at the fact that our neighbor here, Kenya, is it's among the only countries which have gone big to geothermal. So what could be some of those factors holding back its development from your perspective?
Okay, from my perspective, I think first of all, needs, right? Before the convention in France, I think in 2004, where they had emission goals, where they discovered that emission was causing environmental degradation or sustainability problem, then they started thinking of like diversifying. Geothermal it was a possibility. So needs is when you need something, you begin to think of innovative ways to come up with creative solution. I would say needs. I would say, thank God you mentioned Kenya being at the forefront of it in Africa. It means it works. It's just uh, um, things that are needed to be put in place to make it bigger, to make it adoptable everywhere. Technology, policy, government, interest, and knowledge. So people who are interested, are they coming to the forefront of it? Intensive capital costs. The initial capital cost might be comparatively high compared to drilling a conventional well. So, and it depends on technology as well. Like our tools were designed for low temperature cases. Now we're going higher temperature. So these are some of the things that needs to be researched into, solved before and agreed on before geothermal can be adopted everywhere in a really large scale. So yes, government has a role to play in terms of policy. People have a role to play in terms of interest and research. Universities and institutions have a role to play in terms of technology and technology transfer as well as adoption. And now that we have the need for it, is the right time to push it and to utilize it. Yeah.
I agree. I agree. Thank you. Thank you very much for that response. We had some few questions from the chat. I'm just going to read them right away, then we can also address them. The first question was from John. John was asking if the slides could be shared for knowledge
Yeah.
purpose.
Paul has the slide. Paul can share that.
All right, Paul will guide us on how those slides will be shared and how the team can actually access those slides, the team on the call. The second question was from Asasra Asel. His question was, what about the geothermal systems hosted by the carbonate rocks? Isn't there a threat as it would increase the carbon footprint? Oh, the question seems to be quite interesting. I don't know if I don't know the context that you actually meant, but perhaps you can give us your overview and your understanding of it.
I'm not sure I understand. I understand it completely, but carbonate rocks hosting geothermal systems, carbon footprint. So I don't know. I don't quite understand the question, but I'll try to just answer. I'll say that the carbonate rock is basically the nature of the formation. It doesn't have anything to do with the carbon produced from the
Yeah.
system. So we have
Yeah.
oil and gas systems that are situated in carbonate rocks. I'm not sure about geothermal systems in carbonate rocks, but if they do exist, then they're not producing carbon because they are in that formation. They will produce carbon if the constituent from the energy they produce is of carbon, like fossil fuels. But geothermal energy only requires special fluid like water or high temperature fluids to go in there, and they don't need to burn them or create carbon in any way. So no carbon footprint.
Hey, thank you for that. Perhaps he may need to further clarify on the question, but thank you that actually I think it gives him a good understanding of the difference between carbon footprint and the carbonate rocks. So the next question came in from John, and John was asking what design and addition is to be put in downhole drilling tools that will be suitable for geothermal well drilling.
I think this is dependent and specific to what forms of geothermal you're using, if it's a closed loop or an open loop. But either way, the only thing is that your tools and casing and tubings and tubulars should be able to withstand the temperature, and materials as well, because your drilling fluid, your cement, everything should be able to withstand the temperature. I think that's the additional design that should go in. I mean, there are others, but this is just one of them. Yeah.
Okay, thank you. I'm still seeing a lot of similarities with our conventional wells in oil and gas. Very interesting. The next question came from Chukwidi. Chukwidi was asking, he was saying thank you very much for that section, for the lecture. And his question was, what are the costs associated with exploring and developing geothermal resources? And how do they compare to other renewable energy sources, judging by the fact that not all regions have suitable geothermal resources?
I'll let my professor go on this one.
You're trying to give me all the difficult ones to me. As I said before, the cost associated with geothermal is mostly in drilling. And if you go deep in anywhere, it's hot. So it's relevant to the depth, which means you need to drill deeper, which is going to cost more. So again, right now it's not comparable to perhaps wind and solar, but it has a lot of strength because of the stability. It's not periodic. It's stable energy production. And if we can chop down the drilling costs, then it's going to be compatible. And also, if we can drill faster, deeper, then probably will be applicable to any areas. Thank you.
Thank you. Thank you, Dr. Joe. We shall go to the very last question. Okay, there are a little bit more coming in, but let's just quickly go through them. The other question is from Emmanuel, and Emmanuel was asking, so in terms of the general economics, mainly on LCOE, I don't know what they meant by that. How profitable can this be, even if we want to repurpose depleted oil and gas wells in hot rocks?
So repurposing oil and gas wells is quite interesting. I didn't go deep into it, but it depends on also the temperature of the well. So
Sorry about that. You can continue. I've muted the person.
I also don't have any idea what LOCE means, but it's always profitable in the long run if you can diversify your energy supply source. Like we've presented, it's always profitable. And we can see from the other economies, developed economies, as we term them, how diversified they are and how profitable it is in the long run. So I'm not quite clear on the question. So I would just say repurposing oil and gas well is going to diversify your energy supply, and in the long run, it's going to be profitable.
Okay,
Yeah.
thank you. Thank you. The next question was from John asking, can Tricon bits be suitable to? I think this one was already addressed in the previous questions. I think PDC bits have been found to be more effective and more efficient than the Tricon bits. But I would also want to think the Tricon bits perhaps would also come in somewhere, depending on the nature of the lithologies that are being drilled through. Because usually it should be a comparison of the performance here of the bit vis-a-vis the lithology, which it's actually drilling.
Yep, you're right.
Okay, thank you. Then we had another question from Kachi. Kachi was asking, does the use of ionic liquids as geothermal heat carriers pose any adverse effect to the life of organisms and the quality of soil on the surface?
Yeah, that's a good question. There have been concerns on the environmental applicability of these fluids, but to circumvent that, we also tested additional fluid that are not ionic in nature. So we just basically, the results are the same. So they're able to tune these fractures in terms of their temperature and viscosity. So yes, that could be of concern, but as it stands, there's always going to be concern, right? We want a sustainable environment. We want a sustainable space, a sustainable environment. So geothermal heat doesn't pose any challenge to organisms or the life or soil quality, but your choice of material is very important. I would say that there's always room for better research, better research, better materials, better solutions to problems. As we go, the answers we have today will be questions for tomorrow. So we keep improving on those. We keep improving on that. That's what I can say to that question. I don't know if my prof has
Let me add really quick. The goal of EGS is having a perfect or sealed system that your fluid doesn't really leak or cause or get interactive with soil. So it only interacts with the reservoir system, and then it only follows the casing or the wellbore, and then it circulates back in. So in terms, it's sort of like a closed system as well if you design it well. So obviously, if there's an accident or something, it might interact with soil, but our goal for EGS is not to have any interaction of fluids with the soil on the surface.
Okay, thank you very much. There is another similar question here from John asking what are the modifications and additives to add to the drilling muds in brackets, oil-based, to drilling geothermal wells. Maybe I can say something very small about this before Israel comes in. I think
Yeah, Andrew, just
looking at the fact that you're looking at high temperatures, I think HTHP additives become very, very, very important in your drilling fluid to minimize on the filtration losses. So that is from the drilling standpoint of view of the conventional wells. But maybe Israel can also come in and add something onto that.
yeah, you've answered right. So modification will be mainly related to temperature. You want your fluid to be able to withstand the high temperature of the formation. I think that's the difference. Yeah, you're right.
Okay, thank
Let me
you.
let me quick so let me
Yes,
add on
please.
quickly. So currently a lot of drilling is using water-based mud, not oil-based mud. And the formation of granitic hot rocks are typically really low perm and low porosity. So we don't really worry too much about leak off at this moment.
Hey, thank you. Thank you for that. Then lastly, we shall have a question from Benja. Benja is asking, okay, I think his question is slightly answered a bit, but we can go through it as well. High temperatures pose high pressures, high pressure risks. How will this be mitigated during drilling? I would want to quickly, I think, respond to this still from the drilling point of view. I think usually when you're designing your trajectory or your well profile, you really put into consideration all the aspects of pressures. And you must ensure that at all times you have sufficient well control barriers during the drilling operations. So I think during the drilling operations, you have your BOP equipment, which is actually rated to the anticipated surface pressures. So this can guarantee your safety. But in addition to that, following all the standard practices for proper well control. So I don't know if this would sufficiently address that, or Israel or Dr. Hunjo could add something more to this.
Yeah, you're right. So high temperature means you want to go higher depth because, of course, with higher depth for the same gradient, that means you require higher pressure. But like Andrew said, you have to stay within your mod window. You have to stay within your safety window, so you don't go um, above the pressure or like the required pressure for whatever section of the hole you're drilling. So yeah, I agree. I agree with Andrew. Yeah.
Okay, thank you, Israel. Well, I think those will be all from the chat. And
Yes.
the very, very, very last question from myself, just as I've been saying that I'm seeing a lot of similarity with the technology that is currently being used in conventional oil and gas drilling, even the geoscience that is being used. So I'm going to ask this question for the sake of all the YPs who are on this call. If Israel and Dr. Hunjo, you were to give one piece of advice to the young professionals who are on this call with us today, looking to engage into the geothermal energy, what would that be? And what do you think will define the success of the geothermal projects in the next decade? Technology, costs, or policy?
Doctor, you want to go first or should I go?
You can go first.
So I would say if you would take anything from the talk, you should go with the fact that geothermal energy is possible anywhere. It's possible anywhere. It just depends on what you can handle in terms of tool, cost, investment, and depth. And what I think would be the turning point for geothermal energy is people. What I mean when I say people is people who are willing to research, people who are willing to make the right policies, people who are willing to make the right investment, people who are willing to talk about it, people who are willing to, who are happy to research about it. So the turning point for geothermal energy to be applicable in a large scale and useful everywhere is people who would do what I just said. Thank you.
Thank you.
I guess my tip or to a message to the engineers are engineering principles are still the same. What you learn in class, what you learn in oil and gas still applies. So fluid flow through rocks, formation, integrity, everything, formation characterization, everything applies. It's just a different condition and different rock type, which makes it more interesting that you can apply your fundamentals to a different type of problem and solve that. So I encourage all of you to stick to the fundamentals, learn a little bit more, and go into deeper and understand the fundamentals rather than just application. So that's the first tip to the engineers. For the scalability and application of geothermal in the future, I think it has a big potential. One of the things that we often forget as engineers are the perception of community. Everything that we do, everything that comes out as a policy and regulation also comes from the community perception. So knowing well and also as you engineers trying to communicate well with people is going to be a big key. So if they're just I also had a lot of interviews with a lot of people on CO2 storage, and they were talking about some things that I never even thought about that was a worry for me. I guess transferring knowledge well, communicating well will be a big key for implementation of geothermal as well as the oil and gas success in the future. Thank you.
Hey, thank you very, very, very much, Dr. Hunjo and Mr. Israel. Thank you very much for the wonderful responses to all the so many questions that have been asked. I think from the tone of questions that have been responded to, it clearly shows that the lecture has been very, very engaging, and I'm very sure there would still be a lot more questions, but because of time, we shall actually have to close our Q&A. Perhaps Israel and Dr. Hunjo, you could perhaps share your contacts with all the personnel who would want to reach out and ask or engage further onto this topic, looking at the fact that it's a very new one for many, many of the people, especially here in Africa. I think before we do anything further, we are supposed to take a group photo. So I'm going to kindly request all of us here to turn on our videos. We turn on our videos such that we can have a group photo. Please don't be camera shy. Turn on your videos. We take a group photo, all of us.
I don't want me to turn on my video. Let me turn on my own.
Yes, we're waiting for everyone. Just trying to get this ready. Okay, yeah. Some people have not yet turned on their videos. Please, please, please. Cameras. Okay. All right. You say some cheers. Okay, I'll be moving through the different sides to get as many of us as possible. Okay. Okay, let me just check if we have everyone here, just to ensure that we have everyone here.
Okay.
I'm going to request, there are some people who have still not turned on their videos. Please, one more last time, everyone, we have this chance to turn on our videos. Paul, Gideon, Kachi, Juliana, please turn on your video such that you can have this group photo. Yes. Okay.
Is it
Amwa
done?
still yes. Gideon, yes. Okay. All right, we shall go with these ones.
Okay.
Thank you all. Thank you all. Thank you all. So we shall be going on to I think the very last item on our agenda, and that will be having the closing remarks.
So before then, sorry, can you hear me?
Yes, Paul, we can hear
Can you
you.
hear me? Because before the closing remarks, we still have to present the certificate and the announcement we have.
Ah, yeah,
So let's do
sure.
it.
Sure. Let's have that quickly. Then we go to the closing remarks. Just
So
share this.
could you put up the slide so that the actual parties can go ahead?
I get this. Okay, you see my slides?
Yes, we All right, I think go ahead.
Patrick, over to you.
All right. Good evening, everyone. Please confirm you can hear me.
Yes, we can hear you loud and clear.
All right. My name is Akwago, YP Professional SP Worry Section. So I would like to sincerely appreciate Dr. Lee, the excellent presentation, the excellent technical lecture on leveraging geothermal energy for a sustainable low carbon economy. And what really stood out for me was how he really emphasized on the fact that we can actually, move to a low carbon economy as Africa, and it just depends on how diversified a country is in terms of its energy portfolio, right? So I believe it's quite an insightful session. And personally, Israel has been a friend and a mentor since university days, so it's led to attend such insightful lecture. And it's to end I would love to present this certificate of appreciation on behalf of the SP Worry section, as well as the SP Uganda session. We want to sincerely appreciate you, Mr. Ifeomomo and Dr. Onjoli, on the technical lecture, and we look forward to more collaborations in the nearest future. So thank you very much once again, and over.
Thank you.
Thank you. Thank you, Patrick, for that word of thanks. Thank you very much. We are done with the photo. Let's have the SP awareness and upcoming events. Over to you, Emmanuel.
Okay. Good evening, everyone. Can you confirm that I'm being heard?
Yeah, we can hear you loud and clear.
All right. Thank you very much to everyone who have stayed on the call. Thank you to our speakers today. So just to remind us of some of our upcoming programs that we'll be having. By next week, 14th of November, we'll be having another technical lecture program, which is termed Process Engineering for Sustainable Upstream and Midstream Operations. Dynamic and relevance. It's a session that you wouldn't want to miss. We are seeing a lot of process and diversifications of portfolios going on in the Nigerian energy sector. It's a pivotal tool for every engineer and even scientist to have, regardless of if you're in the process side or not. It's a fundamental tool that we should have, and I crave our indulgence that we should turn out in numbers that we have here and even more than to attend that program. for that session. Also on the 21st of November, we also have another technical lecture, which is Leadership by Excellence, Building Capacity Through Intentional Service, roundtable talk with SPA Warri past YP chairs. So this is an avenue for our SPA previous YP chairs to come around and give us talks about leadership par excellence. Many of us here are aspiring to be YP chairs, section chairs, and even council chairs in future. And this is an avenue for us to catch up with some traits, some information that we can get, to be able to as well become leaders by ourselves tomorrow. So that will be all for the upcoming events. We please tell a friend to tell a friend to tell a friend to renew their and join SP. If you are here and you have not yet renewed your membership, either student or YP, please do that before you leave the call today. It's very important. And thank you very much, everyone, once again for staying till this time. And I really appreciate our dedication. So I will as well just bubble up to give the vote of thanks and closing remark, right? So on behalf of the section chair and the Warri section chair, that is Dr. Daytona, and the Ugandan section chair, Engineer Gideon, we're saying a really, really big thank you to the presenters today, Mr. Israel. Just as Patrick mentioned earlier, he is a prodigy, is a alumni from our great institution. So I'm very proud to have him on the call. This is just an intent to what FUPRI can do. So if you have a kid, a family, a friend, tell them that they should come to FUPRI. We have evidence of good alumni here, and also to Dr. Honcho Lee. I mean, this particular session, even if you are asked to pay some good money, I understand. I believe that most of us will pay that without any hesitation. But this is what you're getting for free. One of the benefits of also joining SP and being an active SP member, which say very big thank you to you for your time, your efforts, bringing your knowledge, sharing your knowledge with us here. It's something we are really grateful about. I also want to thank the section chair of the various sections, the Warri section chair, the Ugandan section chair, for bringing together this very important technical lecture session. I want to thank the program chair, the YP chair, the student coordinator, the technical lecture lead in person of Mr. Paul
different section have their this
who
thing,
is
so you
also
can join
here
them.
on the call, right? So for the both sections here, their technical lecture lead, their program chair, I want to appreciate everyone. Time will fail me to begin to call the names one after the other, but your efforts are not going unnoticed. Thank you very, very much. And also to our amiable students and YP, since 5 o'clock still on the call. It shows the hunger and the desire to grow in knowledge. I want to say thank you, keep it up. And we know that one day, all this you've been learning, you've been saying is going to make the difference between you and your peers. So thank you very much, everyone, once again, and do have a wonderful evening or afternoon, as the case may be. Yeah, so thank you very much. Back to you.
Bye-bye.
Yeah, Mr.
Thank you very much, Emmanuel. It's evening here in East Africa, and I think that will be the very, very, very end of our lecture today. God bless you all. Yes, bye-bye.
All right, bye. Yeah, thank you. Till next time. Yeah.
Thank you all. Bye-bye.
Yeah, thank you. Bye.